Hello, AP Environmental Science. This is Unit 7, Part 2. Main focus here is to talk about smog and smog formation. So smog actually comes from combining two words. It comes from combining the words smoke and fog. So put those two things together, we get the term smog. So what you need to know for the AP test is photochemical smog. Well, photo means light, and then chemicals obviously referring to the chemicals in here. So these are reactions that happen in light and specifically sunlight. So photochemical smog is made up of these things. These are components we talked about in part 1. So if you take some NOx in the atmosphere and you add in some VOCs, and then you add in some sunlight, that produces ozone, which is the main component of smog. Okay. Remember, ozone in the troposphere near the Earth is bad because when we breathe it in, it's a respiratory irritant. Ozone up in the stratosphere is good because it protects us from the UV radiation from the sun. But this is a chemical equation that might show up on your test, or you might need to explain this. So NOx, again, usually comes from combustion. In an ideal world, when we burn fuel or hydrocarbons, so for instance, gasoline is C8H18. Ideally, that would mix with just the oxygen in the atmosphere to make CO2 plus water vapor. So that's in an ideal chemistry situation. However, our atmosphere is not just oxygen. It's only 20 to 21% oxygen, but you also have nitrogen in here as well. So let me change colors really quick here. So if I add in some nitrogen from the atmosphere and some VOCs as well, and scientists don't totally understand all of the chemical reactions that happen here because they're very complex, but we do know for sure that there's 78% of nitrogen in our atmosphere. And then some of that nitrogen that gets drawn into our gasoline engine in our car or internal combustion engines, they mix with the oxygen and make NOx. And then ideally you would make just CO2, but sometimes due to incomplete combustion, we also get CO there as well, and some other pollutants as well. Gasoline is a VOC, so this is a VOC here. And sometimes not all the gasoline gets burned, so that gasoline comes out here on the other side or comes out of our tailpipe as well. So you can see internal combustion engines, as far as smog goes, they generate the NOx, they also generate the VOCs. You mix that together in the presence of sunlight and you get ozone. So smog is only a problem during the day because that's when the sun is out, and that provides the energy that drives some of these secondary reactions, which we'll talk about in just a second. You don't get ozone generated at nighttime or once the sun goes down because that sunlight component is missing there. So it's important to understand that because you may have to explain why ozone or smog is not generated at night, and that's because you're missing this sunlight component. And your explanation could just be this chemical equation here. Okay. All right, so primary pollutants. This is very similar to what we've already talked about as far as point source and non-point source goes. So primary pollutants come directly out of the tailpipe. So this is pollutants or chemicals that are formed in your engine, and then they come directly out of the tailpipe. So this is before the sunlight has an opportunity to take effect. So some of the primary pollutants would be unburned gasoline, which again is a VOC. You also have NOx emissions or primary pollutants as well. If you're burning coal, SOx emissions would be a primary pollutant because those get formed in the boiler at the power plant. So stuff like VOCs, NOx, SOx, those are things that are considered primary pollutants because, again, they're formed in the combustion chamber and they come directly out of the tailpipe. Secondary pollutants form in the atmosphere. I'm just going to write air for short. in the presence of sunlight typically. Okay. Not all of them have to have sunlight, but a lot of them do. Okay. The ones that don't are the NOx and SOx that make acid rain, the nitric acid and sulfuric acid. Those are secondary pollutants that just form in the atmosphere as a result of rainwater. Okay. So these form in the presence of sunlight from the primary pollutants. And I also should have mentioned that we would have some ozone in our atmosphere even if we got rid of all our cars and our power plants and stuff like that, because NOx are generated by lightning, so there are non-anthropogenic sources of NOx. VOCs, we'll write down in your notes in a minute, are also formed by plants or trees specifically. So all of this stuff has a natural component as well as anthropogenic or a man-made source of components as well. Okay. So the secondary pollutants that you need to be familiar with, there's 4 of them. The first one is the one I already mentioned, which is ozone. Again, that's the secondary part of the second side of this equation up here. So ozone, which again is O3, is a secondary pollutant. Another one is called PANS for short. And that stands for, actually, just call them PANS. I think I put in your notes what it actually stands for, but we'll just leave it for that. And then nitric acid and sulfuric acid are the 4 secondary pollutants that I want you to be familiar with. Okay. All right, so like I just said before, some of these things are natural sources, so natural emissions of some of these pollutants. So for instance, volcanoes put NOx in the air. They also put SOx in the air as well. And particulate matter, which again is dust particles or smoke. So when a volcano erupts, that'll throw a lot of dirt in the form of microscopic particles or dust particles into the air. Lightning mainly produces NOx emissions because when a lightning bolt zaps through our atmosphere, it has enough energy to break the nitrogen or the N2 gas in our atmosphere into N, and then some of that will combine with the oxygen in our atmosphere to make NOx. Forest fires are a source of carbon monoxide as well as particulate matter, since the smoke from a fire would be considered particulate matter. And then living plants are released VOCs. And actually, about 89% of all VOCs are come from trees. Probably the best example of that is if you get a real Christmas tree and you put it in your house, you know how it smells good? Well, that smell is a terpene that's coming off of the tree that is a VOC. So because you can smell it, you know it's going through the air and it's getting into your nose in the form of something that you can smell, which is a volatile organic compound. So we'd still have lots of VOCs in our atmosphere even if we got rid of all our cars. Okay. Another thing to know, especially, is that geography affects pollution. So this is especially true in the Los Angeles area and other places as well, like Salt Lake City, Utah in the United States. The formation of smog is heavily dependent on geography. So for instance, in California, let's see if I can draw kind of a picture of California here. Los Angeles is located right here. And the Pacific Ocean's out here. Because the wind usually blows off the Pacific Ocean into this LA basin. Let me draw a blown up diagram of this now. So in the LA basin, we have the ocean out here. There's mountains all around the LA basin, and those high mountains actually trap these pollutants in here. So when the ocean breeze comes in here, which it normally does, and there's a whole bunch of cars driving around in these areas and letting these emissions out into the atmosphere, all this stuff gets trapped here. So the pollution or the smog in Los Angeles is particularly bad because we have a lot of automobiles and we also have these mountains. That's different than where the DFW Metroplex where we live is. We do have lots of cars. but we're not surrounded by mountains. So when our cars put pollution out, a lot of that just blows away and gets dispersed because it's pretty windy here in Texas and we don't have these mountains trapping all those pollutants as well. So geography affects pollution. In Salt Lake City, it's kind of the same thing. Salt Lake City is built in a valley. It's surrounded by mountains. There's not as many cars there, but there's enough cars and industry to put these pollutants in the air, and it gets trapped there. In addition to the snow, fall as well, which we'll talk about on the back of these notes, can sometimes create an inversion layer. So places that are colder or where you have a cooler ocean breeze coming in, that can create what we call an inversion layer, and that's another thing that traps pollutants as well, which is on the back side of these notes. So for a thermal inversion layer, we're going to put one diagram here. This is what's normal. And this is what happens when you have an inversion. So what's normal is when the sun's rays hit the ground, that heats up the earth. So it's going to be warmer near the ground. And then it gets cooler as you go up in the atmosphere until you get higher and higher up, and then it gets really, really cold. So this is what normally happens. The hot air rises. Right? That hot air rising can take any pollutants that are down here near the surface of the earth or in the troposphere and dissipate them up into higher levels so that we're not breathing that stuff anymore. So that's what normally happens. Okay? In an inversion layer, you still have the ground here that's heated up by the rays of the sun coming in, but now you have a colder or cooler air mass here and a warmer air mass above it. So usually you see this in two places. Again, if there's snow covered on the ground like there is in Salt Lake City a lot during the winter, that cold snow will cool this air down and then the warmer air actually goes above it. Or in the Los Angeles basin, when you have that cool air coming off the ocean, that'll form this cool air here and then a warmer air here, and then eventually it gets back up to the cold when you get up to enough altitude. So that actually traps it because warm air rises, but cool air likes to fall, right? So that traps pollutants here and makes the pollution even worse. Okay. When you see a smog alert or they come on the news and say there's bad air pollution, they're really talking about ozone. That's what they're looking for. And where we live in the DFW area, we do not meet the federal guidelines for ozone in quite a few days out of the year. So for instance, Los Angeles, they may not meet the federal requirements that say that the air is safe to breathe for maybe 100 days out of the year. For the DFW area, maybe 60 or 70 days out of the year where we don't meet that particular one. And remember, the sunlight drives all these reactions. So you're going to have more pollutants typically in the summertime because there's more sunlight or direct sunlight out there to be driving those chemical reactions. Okay. All right, for acid rain, luckily you guys don't have to memorize these, but you may need to explain what this is. So these are the two equations. We'll do one for sulfuric acid and one for nitric acid. So it's actually two steps. Again, you're not going to have to memorize these because you can use these on your notes. So you have SOx, specifically SO2, that's a gas in the atmosphere, plus the water vapor or the rainwater, that's a liquid in the atmosphere, can combine to make H2SO3, and that would be an aqueous solution or mixed in with the water. Hopefully you know those abbreviations from your chemistry class. If not, the G means it's a gas, L means it's a liquid, AQ means it's mixed with water in an aqueous solution. Okay. And then you take two HNO2s plus the oxygen in our atmosphere, and this would be in an aqueous solution. The gas would be the oxygen in the atmosphere, and that combines to make two HNO3s, which would be in an aqueous solution, and this is nitric acid. And the two just means there's 2 moles of it, or 2 molecules of it, depending on how you want to look at it. Okay. So, whoops, I did that wrong. Hold on. Let me erase that last part. I just mixed nitric and sulfuric. Sorry about that. So the sulfuric acid, so now we take 2 of those H2SO3s that are in aqueous solution. We combine that with the oxygen that's a gas in our atmosphere, and that makes 2 H2SO4s, which would be in an aqueous solution, and this is sulfuric acid. So again, the simplest way of writing this is SOx plus water makes sulfuric acid. And you might be able to get away with that. It depends on how they ask the question. If they say give a chemical equations, then you want to quickly find your notes and write this down. Okay. All right, for nitric acid, it looks very similar. You take 2 NO2s, which would be NOx, and that would be the pollutants that are a gas in the atmosphere. You mix that with water, which is obviously a liquid in the atmosphere, and that combines to make HNO3 plus an HNO2, and then 2 of those HNO2s, and I should have written this down, these would be aqueous solutions as well. And then you combine that with the oxygen in the atmosphere, which is a gas, and that combines to make 2 HNO3s, which is in an aqueous solution would be nitric acid. So this is nitric acid. Okay. And it actually makes a nitric here, and then the HNO2 will combine to make more HNO3s here. So you actually end up with 3 moles of nitric acid for this particular overall equation to happen. Again, the simplest way of writing this is NOx plus water makes nitric acid. And again, you may be able to get away with that as far as explaining it on the test. But if they want more chemical equations, then I would go and quickly find your notes and be able to write this down as well. Okay. All right, improving air quality and problems that still remain. So we do have our indoor air pollutants that we talked about earlier this year. These are more considered outdoor air pollutants. So because our cars drive outside and stuff like this, this would be considered outdoor air pollution. So improving air quality, one thing we've done that's really, really well is get rid of the lead. So lead in air has dropped dramatically. So it's really not a big concern in the environmental movement anymore because we've gotten rid of the lead in our gasoline and gotten rid of the lead in paints and stuff like that. So this is actually one of the success stories. Due to the catalytic converter that we talked about later on, or that we'll talk about in part 3 of these notes, the NOx has gone down and the the CO has gone down as well. So these have dropped somewhat, but not nearly as much as lead. So, and again, that's mainly due to the catalytic converter, which we started putting on cars in the 1970s, and we'll talk about that more in part 3 of these notes for Unit 7. So we've done a pretty good job there as well. What we still need to work on is particulate matter is still a problem. Again, especially the fine particles that can get deep in your lungs and cause problems like respiratory irritant or maybe potentially cancer if it irritates the lung tissue enough. Ozone is also still a problem because it's still being generated because we still have NOx and VOCs as well. So usually when we try and get rid of ozone, we try and get rid of NOx and VOCs. So a lot of legislation is aimed at reducing NOx and reducing VOC emissions because that will in turn reduce our ozone in the atmosphere. Okay. All right, that's it for these notes. So hopefully a lot of that makes sense. If you have any questions about it, you can look up more videos on air pollution or smog. The Bozeman Science ones for AP Environmental Science are pretty good videos to watch as well. Luckily for you guys, you don't have to memorize these equations. You just need to have this thing handy in case they ask you about it on the test.